Hello everyone. Hello everyone. So today our lecture will be on abstract algebra on cyclic groups. This will be a classic blackboard teaching and hopefully it will be useful for you. Please leave a message in the chat if you are online. I think it's time. Shall we start? Okay. So hopefully we will recall a bit of basic definitions and then move into defining cyclic groups. Now, a non-empty set G along with a binary operation is said to be a group if it satisfies four axioms, namely closure, that is, given any A comma B in G, A star B belongs to G. Associativity, that is, given any A comma B comma C in G, A star B star C equal to A star B star C. That is, operating any way doesn't matter. That is, if you can switch the brackets in whichever way you wish. Third is existence of identity. That is, there exists some E in G such that given any A in G, A star E equal to E star A equal to A. Okay. Then existence of inverse. That is, given any A in G, there exists some B in G such that A star B equal to B star A equal to identity. Okay. Now, if a non-empty set along with this binary operation satisfies these four axioms, we call that set, we assign a structure to that set and we call that to be a group. Now, we also saw what is meant by an abelian group. An abelian group is a group which satisfies one more extra axiom, which is called the commutative axiom. Commutativity. That is, given any A comma B in G, A star B equal to B star A. That is, operating, if we have any two elements, operating it either way doesn't matter. If it satisfies the fifth axiom, we call that group to be an abelian. Right? So next we saw what is meant by a subgroup. A subgroup is a subset of G if H is a subset of G, and if H satisfies all the group axioms again, then we call it to be a subgroup. Okay. Now, so our next aim is to construct new subgroups, and before moving into constructing new subgroups, we are going to quote a result which is going to be helpful in proving a subset to be a subgroup. This please note it down as a result. Let G be a group H subset of G if for every A comma B in H, number one, A star B belongs to H, and number two, A inverse belongs to H, then H is a subgroup of G. That is, if we have any subset, it is enough to check whether the subset satisfies the closure axiom and the inverse axiom. It is not necessary to check the associativity and identity, as it will be a consequence of these two axioms. So this is the main result which you are going to use to prove whatever subset we take to be a subgroup. Now, our main focus today will be on cyclic groups and how it behaves. So, given a group, our next aim is to construct new groups from the given group. That is subgroups or a group which is bigger than that or everything. So we are going to construct new subgroups using a given group. Right? So one easier way of creating a subgroup is just by generating elements from a single element. So for example, now what we do is let G be a group. So hereafter we won't write a star in between two elements because it is something like an abuse of notation. We are not going to do use star. It is just if AB, if you write AB, it means A star B. Now choose an element in G. Now given any n in natural numbers, we define A power n to be A star, etc. A n times. That is, we define it this way. That is, A power n will be nothing but A operated n times with itself, depending upon whatever is the operation in the given group. And A power 0 is conventionally defined to be the identity element of the group. And now the next question will be, what will be A power n, where n is a negative integer. Maybe I will use a different notation, say m, where m is a negative integer. So what we define this to be is, we can write it as A power minus of minus m, where minus m is positive. Am I right? We consider m to be a negative integer. We write m as minus of minus m. So A power minus of minus m, where this m minus m is positive. So what we do is, we write this as A inverse star, A inverse star, etc. A inverse minus m times. That is A power m, where m is, that is, for example, A power minus 3 refers to A inverse star, A inverse star, A inverse. So what we do is, we operate the inverse element thrice. where the positive integer part of minus 3 is 3. So we will try to see through examples what is a power n for some given particular groups, and then we move into generating subgroups from this. Okay. Hopefully everything is clear till now. Please don't hesitate to ask any doubts if you have. So now we will consider few particular examples and try to check what is for a given particular element, what is a power n, etc. I think hopefully everyone is for everyone it is visible. Okay, fine. Now, so the basic example which we do when we start with groups is the set of all integers under addition. Now, we will choose an element, say 3 from this Z. Choose an element 3 from Z. Now, we will check what is 3 square. So, our obvious intuition will go on to the square of 3 whenever we do the usual operation of numbers, natural numbers. But here, 3 square refers to 3 and 3 operated in between with respect to the operation given in the group. Now, Z forms a group under addition. So, it is nothing but 3 plus 3, which is nothing but 6. Same way, in general, if it is 3 power say 5, it is nothing but 3 plus 3 plus 3 plus 3 plus 3, 15. So 3 power 5 is 15. Now, the next question is, what is 3 power minus 4? So what we did was, it is nothing but 3 inverse the whole power 4. Now, what is 3 inverse? Inverse of 3 in Z, which is nothing but minus 3, and minus 3 operated 4 times with respect to the operation given here. So minus 3 plus minus 3 plus minus 3 plus minus 3, which is nothing but minus 12. So now, say for example, we will consider one another element, say minus 5. So what is minus 5 the whole power minus 3? Minus 5 the whole power minus 3. So this can be written as minus 5 inverse the whole power 3. So what is the inverse of minus 5 with respect to addition? It is nothing but 5. And you operate 5 3 times. Good Bijal. So in integers, a power n refers to usual multiplication of n with a. So n is an integer, a is also an integer. You are multiplying n and a. The usual multiplication will give you a power n in z comma plus. Now maybe we will move into Zn to see what happens here. Since I have done an example using Z, now please try to calculate in Zn. So maybe I will fix an n. Say I will choose Z8, addition modulo 8. and consider the element, say 4. Find what is 4 power 4 in addition modulo 8. Can you please guess what is, can you please calculate what will be 4 power 4 in addition modulo 8? So what we will do, so we are going to add 4 times and then consider it to be mod 8. Consider it in mod 8. So 4 will be 16 and with respect to mod 8 it is going to be 0. Yes, correct Bijal, it is 0. Param, it is correct. So say for example now 7 power 3 would be not 7 power 3, maybe I will give some other number, 7 power 7. So what will be 7 power 7 in Z8? So what we do is add 7 times, which is going to be 49, and then read it using mod 8, that is divide by 8 and get the remainder, and it is going to be 1. Yes, good. So now if you look at it carefully, whatever we did in examples, whatever power if we calculate is going to be lying back in the group itself. The reason is very simple. Closure property is true in a group. That is, if A belongs to group G, A square belongs to G. Reason is A belongs to G, A belongs to G, which implies A star A belongs to G. So A square is in G. Since G is a group, A inverse belongs to G. So this will imply A inverse star A inverse belongs to G. We can keep on extending this. So what we can say is the set of all A power n where n belongs to Z. That is, this n can vary the set of all integers. That is A power 1, A power 2, etc. It goes on towards the positive side, A power 0. And then towards the negative side, it is A power minus 1, A power minus 2, A power minus 3, etc. It goes on. So consider this set. Clearly, this is going to be a subset of G. So hopefully you are clear with what I am trying to say. Since A belongs to G, A power n for every n in Z is going to be in G. So A power n for every n in Z will be a subset of G. Now our claim is this will form a subgroup of G. Our next claim is this is going to form a subgroup of G. So we will try to prove whether this is true or not given any group. That is, given any group, this set of all A power n where n belongs to Z forms a group, subgroup of G. So we are going to give it a specific notation. We call it G be a group. Consider an element A in G. Now we denote this set to be, we call this as subgroup generated by A. So this is nothing but set of all A power n such that n belongs to Z. Now our claim is this is going to form a subgroup of G. Given any A in G, we can construct a new subgroup using the given element. Now take any two elements in This, well, let us denote it by some h. So what we, as a result I quoted earlier, so whenever we have two elements in a subset, whenever we have a subset, to prove it to be a subgroup, it is just enough to check two axioms. That is the closure axiom and the inverse axiom. Okay. So we will take two elements, say some h comma say r comma s. We'll take two elements in h. Fine. So r is going to be of the form sum a power m, and s is going to be of the form sum a power n. Now rs, whether it will be in h. Now rs is going to be a star etc. a m times. So maybe I should not write this way because m can be even negative. So a power m, a power n. Whether m is negative or positive, this is going to turn out to be a power m plus n. Please try to convince yourself that this is going to be true. Whether n is positive or negative or whatever it may be, this rs is going to turn out to be a power m plus n, because say if both are positive, we will have, if say both m and n are positive, we will have a star etc. a m times star a star etc. a n times. So totally there are m plus n a's. So it is going to be a power m plus n. If one is negative and one is positive, depending upon that, the power will reduce. So rs is going to be nothing but a power m plus n, where r is a power m and s is a power n. Now, since m and n are integers, m plus n is again going to be an integer, because integers forms a group under usual addition. So a power m plus n will belong to h, clearly. Is it fine? Now, given any element, we have shown that the closure axiom is true. So next it is enough to show the inverse axiom to be true. So for inverse axiom, what we do is, since r is equal to a power m, consider the element a power minus m. We don't know whether m is positive or negative. Still, consider the element a power minus m. So clearly this belongs to h, because m is a integer, so minus m is again going to be an integer. Now r a power minus m is going to be a power m, a power minus m. By just now we saw that a power m into a power n is a power m plus n, and this is going to be a power 0. A power m plus minus n, which is nothing but 0. And a power 0 is, we conventionally defined it to be the identity element of the group. And this shows that a power minus m is the inverse of r, because r a power minus m gives us the identity, and you can check that a power minus m times r is going to be identity. So a power minus m is the inverse of a power m, and hence h forms a subgroup of G. So this is the theory part. So let us try to construct subgroups and check how each subgroups lie in given groups, given some examples. Right? So please, if you have any clarifications, please mention it in the chat. Otherwise, you can proceed. I think we can proceed on with examples illustrating this subgroup generated by A. Okay, before moving into that, we will define what is a cyclic group because it just needs this definition. So clearly we saw now this, if G is a group, if subgroup generated by is a subgroup of G, there is a possibility that for some A in G, it's not necessary that there will exist some A such that subgroup generated by A is the whole group. There is a possibility that this forms the entire G itself. Okay, Bijal. Okay, fine. I will write only on the top. Thank you. Now, there is a possibility that the subgroup generated by A turns out to be the entire group G. So, if there exists an A in G such that subgroup generated by A is the whole group G, then G is called a cyclic group and A is called the generator of G. Let G be a group. So we are defining as a cyclic group. So given a group, we can find a subgroup, say subgroup generated by A. We defined it, how we are going to define a subgroup generated by A. Now there is a possibility that it turns out to be the whole group itself. If there exists such an element where the subgroup generated by A is the entire group G, then we have a specific name for the given group. This will be called the cyclic group, and the element with which it generates the group is called the generator of G. So this might appear very abstract to you now. If we look into examples, it will be even more clearer. Fine. Now, so let us consider few examples. Consider integers under addition. Let us consider an element in this group and try to find what is the subgroup generated by it. Now let us consider the element, say 5. Now what will be the subgroup generated by 5? Fine. So subgroup generated by 5 is defined to be 5 power n, where n belongs to z. Now what is 5 power 0? So we will try to list out all the elements in this given set. So this 5 power 0 would be the identity element of this group, which is nothing but 0. Now 5 power 1 would be 5. 5 power 2 would be 5 plus 5, which is going to be 10. Because we saw 5 power n refers to operating 5 n times, where the operation is the operation given in the group. Yes, Mahesh, that is a specific notation given to it. It is called 5 is it. So let us try to check and list out what are all it. Yes, Bijal, it is all integer multiples of 5. Let us try to illustrate it. Write it down and see. Check. Now 5 power 2 is 10. 5 power 3 is 15. And it goes on. Now 5 power minus 1 is inverse of 5, which is nothing but minus 5. And 5 power minus 2 is minus 5 plus minus 5, which is going to be minus 10, and so on. So subgroup generated by 5 will contain the elements 0, 5, minus 5, 10, minus 10, etc. So this is nothing but take the set of all integers, multiply each element with 5, and that is what we are going to get. So we denote this set by 5z. That is, multiply 5 with the set of all integers. So what we get is the set subgroup generated by 5, and which is nothing but 5 is. Now let us check. Say for we have checked what is 5 subgroup generated by 5. Now let us check what is subgroup generated by minus 5. Fine. So let us check what is subgroup generated by minus 5. So subgroup generated by minus 5 is minus 5 the whole power n, where n belongs to z. So we will try to list out. Minus 5 the whole power 0 is 0. Then minus 5 the whole power 1 is minus 5. Minus 5 the whole power minus 1 is inverse of minus 5, which is nothing but 5. Then minus 5 the whole power 2 is minus 10. And minus 5 the whole power minus 2 is inverse of minus 5 added twice. So it is going to be 10. And so on. If you check here, okay, is it buffering? Is it visible now? I think it is visible now. Okay, fine. Now, if we check the subgroup generated by minus 5, it turns out to be minus 5, 0, 5, minus 5, 10, minus 10, which is going to be the same set as what we found out to be the subgroup generated by plus 5. It is going to be the same 5z. So we have tried to infer that the subgroup generated by 5 and the subgroup generated by minus 5 appears to be the same. Fine. Now, so we saw subgroup generated by 5 to be 5z. Now we will check for some other elements so that we will try to guess something even more better. Let us check what is subgroup generated by minus 1. So subgroup generated by minus 1 is minus 1 power n, where n belongs to z. Now minus 1 power 0 is 0. Minus 1 power 1 is minus 1. Minus 1 power minus 1 is inverse of minus 1, which is nothing but 1. And minus 1 power 2 is minus 2. Minus 1 power minus 2 is 2. It goes on. You can check that it covers the set of all integers. So subgroup generated by 1 minus 1 turns out to be nothing but the entire set Z. So we defined what is a cyclic group. What is a cyclic group? If we can find at least one element in this group such that subgroup generated by this element turns out to be the whole group, then we call that element to be generator and we call that group to be a cyclic group. So by this, we can conclude that Z comma plus is a cyclic group, and we found out that minus 1 is a generator. Now, when we check with 5, what we did was we also tried to find what is subgroup generated by -5. Turns out that it is also the same. Now let us check what is subgroup generated by the inverse of -1. So can you please check what will be the subgroup generated by inverse of -1, which is nothing but 1? Can you please check what it turns out to be? So our intuitive notation, when we see this, it is going to be again repeatedly 1. But please be careful whenever you see this notation. So can you tell what is the subgroup generated by 1? Yes, Bijal, it is true. Karparam, yes, it is going to be the same Z. So whenever you saw, till now, we haven't proved it yet, but till now, whatever we inferred was the subgroup generated by an element and the subgroup generated by its inverse happens to be the same. Happens to be the same. So here, when since my 1 generates the entire Z, so we can call 1 to be generator of Z. So Z is a cyclic group, and if you are in need of a generator, we have 2 generators given to us explicitly, which is 1 and -1. Fine. So this is regarding Z, but in between we try to infer something, that is subgroup generated by A and subgroup generated by A inverse happens to be the same, and you can note it down as a result because it is true in general. So the subgroup generated by A, so maybe we can write it down. Subgroup, if G is a group, subgroup generated by A belongs to G, then subgroup generated by A is equal to subgroup generated by A inverse. And you can easily verify it by just seeing the definition. Fine. Now, let us move on to few more examples, how the group looks like and what happens. Fine. So we will look into an example, say Q star under multiplication. Clearly this forms a group. We will choose an element, say 2 by 3. Bijal. So there is a inference from Bijal saying, so any cyclic group will have minimum 2 generators or even number of generators, right? Very good, Bijal. So this is a very good observation, but this is not true in general. So there is a small hindrance here, and we will try to go into it when we do the next example. You will come to know in the next example that this is not true in general. There's a case where it is always true. We need to put up, there is an exceptional case where this is not true. So we have to be careful with that case. Let us come to that in the next example. Fine. So you will, okay, maybe in the next example, I might try to give it to you. Manas, good observation. So A must, whenever A is equal to us, this will not be true. So let us see. Fine. Now, in Q star multiplication, under multiplication, try to find what is subgroup generated by 2 by 3. Or maybe, okay, fine. What is subgroup generated by 2 by 3? Clearly 2 by 3 belongs to Q star. So can you tell me what is subgroup generated by 2 by 3? Yes, Mahesh, it is true. So we will go deeper into it in the next example. So try to find out what is subgroup generated by 2 power 3. Please note it down. You need not mention it in the chat by now because it is not very easy to type, but still, please try to check what is subgroup generated by 2 by 3. So this is going to be nothing but 2 by 3 the whole power n, where n belongs to z. This is nothing but 2 power n by 3 power n, where n belongs to z. Simple. As simple as that, where this 2 power n refers to the usual power. Usual power of n, that is multiplying 2 n times. Whenever it is power minus power, there is a power negative number in the exponent, we take the inverse of 2 and multiply with it. Fine. So this is nothing but 2 power n by 3 power n. Now what is subgroup generated by 1 here? Okay, Manas, there is a good, actually not a, okay, fine. I don't know, everyone have a confusion here. Manas and Karpadam. So I have clearly defined the set to be Q star under multiplication. So if you see here, this set will have 1, 2 by 3 and 3 by 2. That is 2 by 3 and inverse of 2 by 3 under multiplication. Please be careful. We are doing multiplication here. Then 2 by 3 the whole square, which is 4 by 9, and inverse of it 9 by 4, and it goes on. So this is what is subgroup generated by 2 by 3. So it's fine if you make mistake, but still this is the place you learn. So no worries. So this is, so actually the example Manas is the mistake Manas did. We can try to generate an example using that in the later part of this lecture series. We will try definitely come to that part. Please keep it in mind. We'll try to find an example where 2 by 3 power 3 becomes 1. Okay. Now, let us move on to the next example. The very basic example of group. Yeah, Manas. Good question. So I think I wrote 9 by 4, not 9 by 3. Yeah, 9 by 4. It is of the form 2 power n. So what is 2 by 3 the whole power minus 2? So 2 by the whole power minus 2, what we do is, by definition, we will find out 2 by 3, the whole inverse, the whole power 2. The inverse of 2 by 3 is 3 by 2. And we operate it twice. So 3 by 2 into 3 by 2, 9 by 4. Fine. Is it clear, Manas? Fine. Okay, good. So let us move into the most critical and most used example of groups. Zn under addition modulo n. Now, we will fix an n, say n is equal to 6, maybe. Now, let me do one part of it and you please try to do the other part of it. That is, I will tell what to do now. So what we do is Z6 will contain 6 elements 0, 1, 2, 3, 4, 5. Fine. Now what we are going to do is we are going to find subgroups generated by every element in this set. So that is what our aim is now. So we are going to find subgroup generated by every element in Z sets. Now, so let us try to find subgroup generated by 0. So it is nothing but 0 power n where n belongs to Z, which is nothing but you are going to add 0 again and again and again, which is going to be resulting in just 0. Now let us move on to 1. So it is nothing but 1 power n where n belongs to Z. Now it is going to be, say, let us see. First we will try to find all the positive powers and then we will move on to the negative powers. Now 1 power 0 is the identity of the group. So 0. 1 power 1 is 1. 1 power 2 is add 1 twice and read with the modulo 6. So it is going to be 2 again. So 1 power 3 is 3. 1 power 4 is 4. 1 power 5 is 5. And 1 power 6 is going to be 6, which is nothing but 0 here. Now, we need to check the negative powers. Fine. Now, here it is not necessary to check the negative powers. The reason is, if we check the negative powers, it is going to lie again in Z6. But since this has exhausted all the elements in Z6, it is not necessary to check the negative powers. It is going to lie again in this same set. So hopefully I'm clear with what I said. Okay, good Bijal, good observation from the inference from the result I said. So I will repeat whatever I said here. Now subgroup generated by one is 1 power n where n belongs to Z. Now this first we found all the non-negative powers. So 1 power 0, 1 power 1, 1 power 2, 1 power 3, 1 power 4, 1 power 5 we checked. And if you see 1 power 6, 1 power 7, etc., this is going to be repeating. So 1 power 6 is 6. With respect to modulo 6, it is going to be 0. 1 power 7 is 7. With respect to modulo 6, it is going to be 1. 1 power 8 is going to be 8, which is under modulo 6, it is going to be 2. So it goes on. So it repeats. So positive powers are exhausted. Now we come to negative powers. If we check here the negative powers, what happens is it is not necessary to check the negative powers at all. The reason is we clearly check that this will form a subgroup of G. That is, in even more specifically, we can say this is a subset of G. Fine. There are no other elements left out in this subset. So there are no other possibilities of any element entering into this. So this is going to be the entire set subgroup generated by 1. So this turns out to be Z sets. Also, from the result which I said, this is also equal to subgroup generated by 5 because inverse of 1 in Z sets is 5. So what we said, in a group G, subgroup generated by A and subgroup generated by A inverse are the same. Now, if we look at subgroup generated by 2, it is going to be 2 power n where n belongs to Z, which happens to be 2 power 0, which is 0, 2 power 1, which is 2, 2 power 2 is 4, 2 power 3 is 6. With respect to modulo 6, it is going to be 0. So if you repeat in the positive powers, you are going to get again the same elements. And if you try to repeat the negative, if you go into the negative powers to check whether anything comes, you are not going to get anything. So this is going to be just this. You can clearly check that, verify that. And this also happens to be subgroup generated by 4 because subgroup generated by 2 and 4 are the same, as 2 and 4 are inverses of each other. Now the only element left out is subgroup generated by 3. So I will write that here. Subgroup generated by 3 is nothing but 0, 3. Since 3 is the inverse of 3, so subgroup generated by 3 is just 0, 3. Now here we try to infer or try to dig deeper and check something. So we will try to list it down in a particular way so that it is clearly visible. We will try to write. Now in Z6, subgroup generated by 0 is equal to 0. Subgroup generated by 1 equal to subgroup generated by 5 is equal to Z6. Subgroup generated by 2 and subgroup generated by 4 is equal to 0, 2, 4. And subgroup generated by 3 is equal to 0, 3. Now, this is cyclic groups. Here, especially in Z6, we have a very clear property. So in Z6, if you see clearly, the devices of Z6 are 1, 2, 3, and 6. If you see clearly, the devices of 6 are 1, 2, 3, and 6. And if you see here, the number of subgroups of Z6, which we found out, happens to be exactly equal to the number of devices of Z6. Also, for if we need an element, if you need a subgroup of order 1, we have. If we need a subgroup of order 2, we have. If we need a subgroup of order 3, we have. And if we need a subgroup of order 6, we have. That is, for each divisor, there is exactly one subgroup. And okay, so maybe I can state a result and be even more clear. That is, given a cyclic group, every subgroup is going to be cyclic. Given a cyclic group, every subgroup is going to be cyclic. So you can note this down as a result. So since every subgroup is cyclic, these are all the possible subgroups of Z6. So these are all the possible subgroups of Z6. Now, if we see carefully, the number of subgroups of Z6 is nothing but the number of devices of 6. And we have exactly one subgroup for each divisor, having each divisor's number of elements. Now, if we look at it carefully, so maybe I can try to write it for some other end so that it will be even more clear. So let us consider, say, Z12. So there is a discussion going on here, I guess, in the chat. So Karparam, one small doubt, does 0 belong to Q plus? So you mean to say the set of all positive rationals, and please check under which binary operation that forms a group so that you will be clear whether 0 belongs to Q plus or not. Fine. Thank you. Now, Z12. So list out the possible devices of Z12. Sorry, possible devices of 12. So the possible devices of 12 are 1, 2, 3, 4, 6 and 12. So these are all the possible devices of Z12. Sorry, possible devices of 12. Now we are going to find a subgroup having order to be 1, 2, 3, 4, 6 and 12, and this can be easily found out by a particular method. So what happens is Zn has this particular property. So what happens is, so we will try to find the subgroup having 4 elements. So what we do is try to find subgroup generated by 12 by 4, where this division refers to the usual division in real numbers. Fine. So we are going to find a subgroup having 4 elements. So what we do is divide this 12 by 4. We are going to get 3 and try to find subgroup generated by 3. So subgroup generated by 3, if you see in Z12 will have 0, 3, 6 and 9. Fine. So if we need a subgroup of a given particular order, it is possible that we can try to generate it using a method here. That is, say if, for example, if you need a subgroup having just one element, try to find subgroup generated by 12 by 1, which is nothing but 12. With respect to modulo 12, this is nothing but subgroup generated by 0. And this happens to be just 0. Now, a disclaimer, I am doing this keeping in mind that you all are a bit clear about the statement of Lagrange's theorem. The statement of Lagrange's theorem states that if G is a finite group and H is a subgroup of G, order of H will divide order of G. So that is why we are considering only the devices to find order of subgroups. Okay. Now, so you can note it down as a general result in Zn that in Zn addition modulo n, if D divides n, then there exists a unique subgroup of order D, and that subgroup means subgroup, say we will denote it by H. You need subgroup H of order D, where H is equal to subgroup generated by n by D, and order of H is equal to D. So just write it down, right? Please note this down. This will be very much useful. The reason is, whenever we have a cyclic group, we can try to somehow relate it to Zn, and we can just think of subgroups. These subgroups and the subgroups of Zn can be easily found out using this result. So for Zn, the number of subgroups is nothing but the number of divisors of n. So there will be exactly one subgroup for a given divisor, and that subgroup can be found out using this result. Okay. So this is all about Zn. So there are even more crucial properties of Zn. Now clearly we saw that Z6, when we saw Z6 and Z12, if you check that, one happens to be a generator for Z6, and even in Z12, if you check, one happens to be a generator. So in Zn, one happens to be a generator for every n, and hence Zn is always cyclic, and that is why we have this result. So I am repeating from the first. That is, given any n, Zn is always cyclic under addition modulo n. So maybe I will list it down all the examples. Okay, there is a clarification from Bijal, sir, in which all case the number of generators of a cyclic group be surely even in number. Okay, so good question. There was this question earlier, so we will try to look into it now. Maybe. So I will try to first list down all the things we did in Zn by now, and then we will move into the question given there, asked by Bijal. Now, so this is going to be point 3. So the first point is Zn is cyclic. 1 is a generator. Number 2, every subgroup of cyclic group is cyclic, and hence therefore every subgroup of Zn is cyclic. And the third point is, if whenever D divides N, there is a unique subgroup H of order D, where H is nothing but subgroup generated by N by D. Now, in between we had an inference that subgroup generated by A and subgroup generated by A inverse are the same. Now, so let us consider an example where the result stated by Bijal will be a bit tricky to calculate. Now, say let A belongs to G such that subgroup generated by A is G. That is, we are considering G to be cyclic. I think it is visible now. There was a small network issue in between. Okay, fine. Now, consider a group G where this is subgroup generated by A is G. Now, here if A happens to be A inverse, so let us see what are all the elements in G. So this says that multiply both sides with A. So we will get A square equal to E. A square equal to E. So we will have this relation with us. We have not defined anything called order till now. So I am not going into the order part of it. But just let us see using this. So here we have a fact that A square is. Now let us see what is subgroup generated by A. So it will have the identity element. It will have A. So then it must have A square, which is identity, which is again lying in this. Then A power 4, which is A power 3, which is nothing but A square into A. A power 3 is A square into A, which is nothing but EA, which is nothing but A. So if you go on repeating this, you are going to get EA repeatedly. And if you're going to find what is subgroup generated by A inverse, since we have found A is equal to A inverse, these are going to be the same. Actually, A and A inverse are same, so subgroup generated by A and A inverse are the same. So this will be nothing but G. So entire G will contain exactly 2 elements. Now, what are all the generators of this group? Definitely not the identity element. So there is exactly one generator for this group. So whenever we have an element whose inverse is itself, then the subgroup generated by it, if it happens to be cyclic, that is, if G turns out to be the subgroup generated by A, where A is equal to its own inverse, then the number of generators in this group is exactly 1, and you cannot say it is even in number. Now, this happens only when A is equal to inverse and not in any other case. So if we have any element, any generator for a group where G has more than 2 elements, definitely it will have even number of generators. So the result stated by Bijal can be stated as follows. If G is cyclic, where order of G is equal to, order of G is greater than 2, then the number of generators of G is even. The number of generators of G is even. So whenever the group has order greater than 2 and is cyclic, then the number of generators of G is even. So I will just give one more example and then I will wind up. Sorry, I have taken some 5 minutes, it's 7 minutes extra. So let me wind up with one another example and one another inference in Zn. Now we will consider Z7. So maybe I will give you a minute time. Try to find all the subgroups generated by all the elements of Z7. That is, Z7 has 0, 1, 2, 3, 4, 5, 6. Try to find subgroup generated by 0, 1, which has happened to be subgroup generated by 6. 2, which is nothing but subgroup generated by 5. 3, which is nothing but subgroup generated by 4. Try to find all these sets. I'll give you a minute time. It is very easy to calculate. That's why I'm giving you just a minute time. So when I say, you can try posting your answers. So you can post your answers now if you have. If you have calculated, you can post the answers now. So what will be subgroup generated by 0, subgroup generated by 1, subgroup generated by 2, 3, etc. So subgroup generated by 0 will be 0. So for the rest of it, Karparam, good. Mahesh, yes, it is Z7. Bijal, yes, it is true. So what happens is here, we get Z7 for all the elements. So now from this, not just from this, in Z sets we have found out that, so here in Z7 we found out that every non-zero element is a generator. Now in Z6 we found out the generators to be 1 and 5. Now can you try to infer how the generators behave. What are all the generators? Can you give a guess on how the generators behave, or what are all have the property to be the generator? So is there any number theoretical relation between uh, the n we consider and its generators? So try to have a slight guess. Good observation, Mahesh. Others, do you have anything, any observation from here? So my question is, given a n, given a n in Zn, when we look into all its generators, is there any relation between its generator and the n? So here in Z7, what we saw is every n, every non-zero number happens to be its generator, and in Z6, 1 and 5 happens to be its generator. So in general, yes, it is true what Mahesh said. Now consider, so if we need to find the generators of a given Zn, just find all the numbers x such that x comma n have GCD 1. And that x, okay, maybe I will write it down here. In Zn, under addition modulo n, the generators of Zn are set of all x in x such that GCD of x comma n happens to be 1. So these are all the generators of Zn, and the number of generators happens to be 5. And that is why in the previous claim, so you can refer your number theory books, phi of n is always when n is greater than 2. So phi of n is Euler-Taussian function. It gives us phi of n refers to the number of positive integers less than n and relatively prime to n. So phi of n refers to the number of positive integers which are less than n and relatively prime to n. Now phi of 1 is not defined. Phi of 2 happens to be 1, and for every integer greater than, every positive integer greater than 2, it happens to be an even number, and this happens to be the number of generators of Zn. So Zn, the generators are all the relatively prime numbers, the numbers relatively prime to n, and the number of generators is phi of n. And I think we can wind up for today. If you have any clarifications, please post it in the Telegram group so that we can discuss and everyone can discuss. Hope the session was useful. Please stay safe and thank you.